Hello and welcome to Engineer's Mindset. So in this video, we are going to be looking at static friction and kinetic friction on an inclined plane. In the previous video, we talked about the difference between static friction and kinetic friction, link in the description below. Now, let's say we have a mass M which is resting on an inclined plane. A plane is said to be inclined when it makes an angle to the horizontal. Now, we have a mass M resting on this surface. When is the mass said to be under static friction and when is this mass said to be under kinetic friction? Just like explained in the previous video. If this mass is moving up the plane or down the plane, then so far the mass is in motion, it is experiencing what is called friction, and that friction is called static friction. But if this mass is completely resting on the surface, maybe there is a restriction here that makes this mass to rest on the surface and neither climbing up nor down, then we simply say this mass is under what is called the static friction. And in the previous video, we looked at static friction, which is Fs, to be equal to the coefficient of static friction mu x multiplied by the normal reaction n. Similarly, we looked at kinetic friction Fk to be equal to mu k multiplied by the normal reaction n. Now, I said in the previous video that there cannot be friction without two surfaces coming in contact. And when surface comes in contact, there is bound to be what is called a normal reaction, a reaction force which acts at 90 degrees to the surface of contact. So I have that this mass, the surface of this mass is in contact with the surface of the inclined plane. For that reason, we are going to have a reaction force which is at 90 degrees to the surface. This reaction force must always be at 90 degrees to the surface, as can be seen. 90 degrees to the surface, and it is called the normal reaction force. It is called the normal reaction force. Now, because this object has a mass, every object that has a mass must have what is called a weight, and the weight of that object must act vertically downwards. So we have that the weight of this object will act vertically downward. So you have something like this. This is the weight of the object acting vertically downwards, and the weight is always given as mass times acceleration due to gravity. Now, let's say this object is at rest. If it's at rest, that means motion is neither taking place. And two key things can make an object to be at rest. I said all this in the previous video. When the applied force on the object is less than the frictional force, the object is said to be at rest. Secondly, when the applied force is equal to the frictional force, the object is said to be at rest. So let's say the original intention was to pull this object up the plane. That was the original intention by a force P. That was the original intention, but this force is less than the frictional force. Of course, if the intention was to pull the object up the plane, then we are certainly going to have a frictional force which acts to oppose that motion, Fr. Now, in this case, if the frictional force is greater than the force applied on the object, then it becomes a static frictional force. So we simply call that Fs. S for what? Static. Which means this object will remain at rest and neither going down nor climbing up, simply because the static frictional force or the frictional force is greater than the applied force. The same thing happens if the frictional force is equal to the applied force, then this object will also remain at rest. So in this case, we are simply considering the static frictional force. So always keep it in mind that whenever a force is applied to pull an object up an inclined plane, there's always going to be a frictional force that is acting to oppose the motion of that object. So while this is up the plane, frictional force is down the plane. Now, I said something in the previous video that the angle between any vertical line and an incline is always taken as the angle of inclination. The same thing happens here. The angle here, this angle of inclination is theta, but I have now a vertical line which appears to be the weight. But I have another inclined line which appears to be normal reaction. Always, whenever it comes to inclined plane, the angle between the weight and the normal reaction is taken as the angle of inclination, theta, simply because the angle between any vertical line and an incline is taken simply as the angle of inclination. I will do a video on this explaining how this angle is equal to this angle. If you don't want to miss out on that video, then do well to subscribe if you're new to the channel so that when that video drops, you're going to see it. Okay, so keep it in mind always the angle between any vertical line, not necessarily the weight now, but any vertical line at all, and the normal reaction. Any vertical line and the normal reaction or an incline is always taken simply as the angle of what? Inclination. Now, you observe that if I draw an imaginary line and join these together, this becomes a two-force system, a 2D force system inclined. So I can have something like this. This represents my weight. I have my normal reaction here. Okay, I have my normal reaction here, and then I have this joining them together. So this is my weight, and this is my normal reaction. So the angle between the weight and normal reaction is taken as the angle of inclination theta. So which means I can either resolve the normal reaction purely vertically and purely horizontally, or resolving the weight to be what? Inclinedly vertical and inclinedly horizontal. Now, the best approach or method to always use when carrying out analysis on inclined plane friction is to resolve the weight to the incline, because every force on this inclined plane are all inclined. The static frictional force in this case is inclined. The load applied on the object is also inclined. The normal reaction is inclined. The only odd force here is the weight. So since the weight is purely vertical, then it will be wise to resolve the weight to be what? Inclinedly vertical and inclinedly horizontal. Of course, whenever a force is found between two dimensions, there's always a need to what? Resolve that force. Now, let's draw an imaginary Cartesian system and see. So this is now going to be my vertically inclined component. That means this is going to be my horizontally inclined component or coordinate. So this is my inclined vertical y, and this is my inclined horizontal x up the plane. So when motion is up the plane, it's purely horizontal, inclined horizontally, and when motion is down the plane, is also horizontal but inclined horizontally downwards. Okay, so you observe that normal reaction is inclined vertically, but the weight is purely vertical, which means the weight now is acting as a two-dimensional force system, and as such, there is going to be a need to resolve the weight. Now, I always say in my 2D force videos, to resolve any component in any direction, all you need to do is hold the tip of the arrow of the force and pull it to the direction you want to resolve to. If the force passes through the angle in that quadrant to get to the direction you're resolving to, then multiply the force by cosine of the angle it passes through. But if it doesn't pass through that angle to get to the direction you're resolving to, then you multiply by sine of that particular angle. In this case now, the only recognized angle here is theta. Of course, if I want to find this angle, it becomes 90 minus theta. But since there is no given value for theta, let's just maintain it as theta. So if I want to resolve this weight vertically inclined, you hold the tip of the arrow of the weight, pull it to meet the vertical inclined line. Observe that this weight will still be pointing downwards over here. So if I hold the tip of the arrow, pull this weight to meet here, it also points downward. But this weight moves all the way from here to this point, covering this angle theta. Since it covers this angle theta, then I am going to multiply the weight by cosine of the angle it passes through to get to this quadrant I am resolving to, or to this component, which is the inclined vertical component. So that means over here, the weight becomes W multiplied by cos theta, and you have this. Similarly, I need to resolve this weight to also be what? Horizontally inclined, because it is now occurring as a two-force system existing between an angle, or existing between the x and the y component, in this case inclined. So after resolving vertically, there is always a need to what? Resolve horizontally. So to resolve this force horizontally, this is the horizontal component. So you drag it to meet the horizontal component in its own quadrant. And that is what this particular component over here. Again, hold the arrow of the force, pull this force in the middle line. Observe the arrow direction. The arrow points where? To the left or downwards. Okay, the arrow points inclined downwards. But observe that this force moves all the way from here to this point. There is no angle here, or normally the angle that is supposed to be here should have been 90 minus theta, because angle on the quadrant is 90 degrees. So if here is theta, that means here is 90 minus theta. So that simply means this force in the horizontal inclined axis is going to be W cos 90 minus theta, or simply W sine of the angle it doesn't pass through. So since it doesn't pass through theta to get to this quadrant, then it becomes W sine theta. So the component of this force inclined horizontally is W sine theta. Else, you can also call it what? W cos 90 minus theta. So if you know this angle here, you can simply say W multiplied by cosine of that angle over there. So that is the aim, resolving the weight only to be what? Inclined vertical and inclined horizontal. Once you're done with that, you employ your equilibrium equation. Now, what are the equilibrium equation? Simply, summation of force in the x-axis is equal to 0. But in this case, since motion is horizontal, summation of force is summation of the horizontal forces. Since motion is horizontal, when it comes to friction, forces are always positive in the direction of motion. The idea is to always make frictional force negative because frictional force must always act to oppose motion. And any force that acts to oppose the motion of an object is a negative force. So summation of force in the x-axis is equal to 0. Now the idea I said earlier is for this force P to move this object up the plane. This simply means any object that moves up the plane or any force that moves up the plane remains a positive force. And as such, any force that comes down the plane remains a negative force. So you apply this, summation of force in the x-axis is equal to 0. Horizontally moving upwards is considered positive. Horizontally coming downwards is considered negative. So you look at the system, what are the forces moving in the horizontal direction? You have P, which is the force causing motion on this object, moving up the plane, which means P is positive. You put it down, P, and it is positive. Again, you have the frictional force coming downwards. Since it's coming downwards, it becomes what? Minus the static frictional force. So it's always going to be negative. It is always going to give you a negative. Not that when you solve a problem, you're going to have a frictional force to be negative. No. But it's just to tell you that frictional force always must be negative in the equation because they act to oppose motion. Okay. Again, when we resolve, remember that we have W cos 90 minus theta acting down the plane. So we also have W acting in direction of what? The frictional force. So which means this weight horizontally is what? Against the motion. So it's also going to be what? Negative. So it becomes negative W. Either you're using cos 90 minus theta or simply using sine theta, and you have this. So these are all the forces going horizontally. The whole of this is simply equal to 0. So from here, you can solve. If you know your weight, you know this force, you can find your frictional force. Now, let's say we make the static frictional force subject to the formula. Let's simply send negative static frictional force or negative F over to this side of the equation. Negative sign cross and equal to sign becomes positive. So you have that the static frictional force F of x is going to be equal to, I am left with P minus W sine theta. Let's simply call this equation 1. But not forgetting, we said in the previous video that the static frictional force Fs is simply taken as mu s multiplied by what? The normal reaction, already stated here. So the coefficient of static friction multiplies normal reaction. How then do you find your normal reaction? Simple. To find your normal reaction, you employ your second equilibrium law, which is summation of all the vertical force on the system. Now, since motion is not vertical, then we maintain the rule every force that moves vertically upwards inclined is taken as positive, whereas every force that moves vertically downwards inclined is taken as negative. So you employ your second equilibrium law, summation of vertical force, summation F of y to be equal to 0. Since motion is not vertical, then any object that moves vertically inclined is taken as positive, whereas object that moves downwards vertically inclined is taken as negative. So you look at the first system, you observe that your normal reaction is vertically inclined upwards. Okay, as can be seen here, normal reaction is vertically inclined upwards, so it is taken as positive N. But then we resolve this weight also to be vertically inclined, but the weight is pointing downwards. Since the weight is pointing downwards, it becomes negative. So I simply have minus W cos theta, and these are the only vertical components we have on this system. The whole of this is equal to 0. Now, if you have this, that helps you to find your normal reaction, which simply implies that the normal reaction end is equal to send minus W cos theta over to this side of the equation. Negative sign cross an equal to sign becomes positive. Therefore, you have W cos theta. So this becomes my normal reaction. So if I know the normal reaction force, it means you can find your static friction force. If you know the static coefficient of friction, multiply by the normal reaction, and of course, you can find anything you're asked to find in the question. Now, this is just a case of statics when the object is at rest. But there is no much difference between this and when the object is in motion. Of course, let's say there is a force that is acting to pull this object downwards. Now, if this force, let's say we have a force acting on this mass to pull it downward, call that force also P. Call this force P. Acting to pull this object downwards. That means we are going to have a frictional force which acts up the plane against that motion. And if this force is greater than the frictional force, it means the motion of this object will act where? Down the plane. If the force is greater than the frictional force, it means the motion of the object will act down the plane. So you have your friction. In this case now, friction is simply taken as what? Kinetic friction. In this case, the friction is taken simply as kinetic friction, which is the friction when an object is in motion. So if this force is large enough to push this object downward and keep it in motion, then the frictional force acting becomes a kinetic friction. So every other principle remains, only that force should now be positive in the direction of motion. Since this object is acting downwards or down the plane, then force down the plane inclined should be positive, whereas every force up the plane inclined should be negative. That is to make what? Frictional force always a negative force. And if you apply everything here holds, everything we've done here holds. The only thing that is changing now is your frictional force is no longer going to be static, rather it is now going to be what? Kinetic frictional force. But every other principle, every other thing we've done here holds. That's just the basic difference between the two. So for instance now, since motion is down the plane, it means that this law will change. Down the plane becomes positive and up the plane becomes negative. So that simply means my force is causing this object to move in the direction of the force, which means P is taken simply as positive. Again, frictional force is acting to oppose that motion, so it is taken as what? Negative. But frictional force in this case now becomes the kinetic frictional force, which is Fk. Then again, I have that when I resolve the weight, it is now in the direction of motion of P, which means the weight is also coming downwards along with the motion of the block. So which means it is going to be what? A positive weight in that direction. So we have plus W sine theta, and the whole of this is equal to 0. So you see the difference between the two methods. Okay, when the object is coming down the plane, the weight is also in favor of that motion, so weight becomes positive. But when the object was moved to go up the plane, the weight was not in favor, therefore the weight becomes negative. But in all, observe something that is unique. Frictional force is always what? Negative, because it is a force that acts to oppose motion. So even in kinetic friction, regardless of the fact that the motion of this object is coming downwards, so far we have frictional force there, it must always act to oppose the motion of that object. So in this case, our frictional force, though kinetic, is still negative. Similarly, our frictional force here, though static, is still what? Negative. Okay, so the equation basically remains the same. The only thing now is that friction is no longer going to be what? Statics, but rather kinetics. And if you're given the coefficient of kinetic friction, normal reaction remains the same way to find. If you're given the coefficient of kinetic friction, after obtaining your normal reaction, multiply by that coefficient and you have your what? You have your kinetic frictional force. Alright guys, so that's the basic idea behind the static friction and kinetic friction on an inclined plane. In the next video, we are going to be employing everything we've learned here to solving a problem. Alright guys, so I hope you find this video interesting and helpful. Please, if you do, I would like you to encourage my work by liking my videos, commenting nicely, sharing to your friends, and of course, subscribe to the channel and turn on your notification bell to get updates when the next video will drop. I will see you in the next video. Thanks.